So I've been dealing with many different types of organic contaminants for, I guess, about 14 years. Started out with PFCs, like perfluorinated compounds, pharmaceuticals, metabolites. I did cannabis postdoc for different potency, fungal mycotoxins, metals, pesticides now. We do pesticide transformation products in my program, but we'll talk more about that. But right now, most of you have maybe heard of ultraviolet filters. We call them UVFs. The most common ingredient in sunscreen, obviously, for various reasons, but also found in many other products as well. And so what I had done back in, I guess, 2021, my children are 13 and 17 years old. And during the pandemic, we took them to the pool. I saw the outdoor pool was white, and I went, there's got to be a crazy amount of chemicals in here. Duh, right? So let's analyze it. But the problem is there's no methods for it at that time, especially with chlorinated outdoor pools. And so you have this combination of mixed mechanisms of sunlight doing things, the chlorine doing things, the circulation system doing things. And so it was very unique. And so I thought that I looked at my wife and I said, I'm going to buy analytical standards and I'm going to start doing this, you know, and it was pandemic, right? Hi. Ahoy. And so it's spun off into many other projects. So this might be unique to Czech Republic, but for us, our lands of where our university is on, we acknowledge as Canadians now that we had genocided and murdered many Indigenous people in our country. And we are at a point now with what we call truth and reconciliation. So the acknowledgement of what history is, the terrible things that we've done to those people, and that we acknowledge that we are trying to really what they call braid or put together Western science with traditional Indigenous knowledge as well, because for those of you that take ecotoxicology, human toxicology, epidemiology, those types of things, you have a variety of degrees of causation, right? So you've got experiments, you can control variables, figure things out. But you also have observations, ecological studies, observational studies. And that doesn't mean that they're not good. You add all of these studies together from observational to experimental, and you create what's called an accumulated weight of evidence, right? It's really important that you have all of these different aspects of weight of evidence. So not just one thing is better than the other. So we acknowledge that an Indigenous perspective is also really important to traditional scientific. So what kind of work are we doing today in my lab overall? So we are quantifying pesticide remediation and metabolism and transformation in biobeds. Anybody here know what biobed is? No? Basically, this isn't going to work probably. Oh, it does. There's these biomixture, so microbes, soil, peat moss, rocks, minerals, all sorts of different things. And we have these landscape emitters, so these pipes that will drip basically the spray rinseate when you spray farms with pesticides to remediate it instead of just dumping it on the ground and then causing an ecological problem. So we'll back up and then they'll drip through and hopefully remediate and go away, degrade, then get put into a second cell and do the same thing. And then we can calculate and quantify the removal. The interesting thing is sometimes those pesticides can actually go up. So depending on the absorption and depending on other mechanisms, you think you're removing these compounds, but sometimes you can actually get greater concentrations depending on the compound. So it's not always that easy, right? Chemistry. So we also are doing UV filters, which I'll talk about today. The Canadian government and the Manitoban government, where I'm from in central Canada, is very interested because of Trump and his administration and America with fentanyl and all that kind of, but fentanyl wastewater epidemiology is very important. So not only to screen what kind of illicit drugs are in the wastewater, but also to quantify, which is where my laboratory comes in, to know how much illicit drugs are being used per capita per people. So we're national agreements and also local agreements starting up right now. And so we need people to do that. So that's good. Unknowns analysis using headspace analysis with GCMS, gas chromatography, of volatile compounds in flowers. So pollinator attractants, bees that pollinate and grow all of our crops. are attracted to certain smells and flowers, and the volatile compounds are analyzed using different databases, like a profile. And then analyzing the leaching, persistence, the transformation of PFCs, which everybody has heard of, fluorinated compounds, and looking at how buried textiles or even like wastes, or even from like a sustainability aspect, the PFCs will leach into the soil and then get into the groundwater and things like that. So we're going to start to monitor what that looks like. There are lots of, and many, many other projects. So anyway, so we use a lot of chemistry. Oh, no, we don't want to see this. But these are, each one of these is analytical standard. Usually in my lab, green things are unlabeled. And then the usually orange labels, everybody do it right, is internal standards. So isotopically labeled internal standards. And this is, for my program, for the last 15 years, incredibly important to be able to understand where your extraction processes are working, what your losses are like, and if things are fully quantitative. Right? So we have a bunch of instruments. These are just some of them. We have a GCMS here with the headspace analyzer. So we can just put things into the little tray here, and it will automatically cook and vibrate it up and then inject it into this machine. And then we can run unknowns analysis. We have one of, at the time, was one of 4 instruments in Western Hemisphere, all one half of the Earth, that was run on hydrogen from adjuvant. So it's a good instrument. Hydrogen, smallest molecule, acts like an acid, keeps the source of the machine very clean, which is actually a very low back pressure. Not super clean, you still have to clean things, but still it's a good ion. LC triple quad, I've seen many, many here. You have fantastic facilities in České. You have fantastic. So you're familiar with that. We also have an FTNIR. That's dead now. So basically we can run higher concentration things, liquids. We could put soils and solids in there. We have calibrations database that's worth like $100,000 for organic carbon content, for minerals, for butter, cheese, diesel, it doesn't matter, milk, wine, beer. There's so many things that you can look for certain components, proteins, carbohydrates, sugars, metals, whatever. And so you use other gold standards, other machines, tell this machine based on its spectra what it is, and you can create calibration databases. Keep building. So we have all sorts of things. We also have an ICP-MS for metals. And we also have a new LC single quad with refractive index to do like higher concentrations in foods and things like that as well. So we keep growing, which is great. As an environmental chemist, as an analytical chemist, I know not everybody here is, but for me, it's absolutely critical that the information that you're going to get out of a mass spectrometer, as many people I've talked to here know, is only as good as the information and the materials you're putting into this machine. I said before, you wish you could walk up to the machine and say, give answers, and then it will just show up, and it doesn't work like that. And it's very disappointing to people. It's not like that. So it has to do with extraction process. How can you take what you want to target out of very complex matrices, whether especially plants with pigments and bioflavonoids, all sorts of crazy gunk that you don't, wastewater, sludge, environmental things, proteinaceous things become very problematic for getting what you want. Separation techniques. How do you take what you want to separate it away from all the other things that you don't want? How do you confirm what you found? How do you quantify how much you have found? And all of that has to do with validation. You have to, and the most important thing to do is to decide what type of validation criteria you are using. So if you're using EU, we use Eurochem guidelines, US EPA, Health Canada guidelines, different pharmacopoeia, British pharmacopoeia, American pharmacopoeia. There's a bunch of different guidelines, right? So you choose a set of guidelines that you want to use and you stick to it and you fulfill those criteria. And what that looks like is specificity, trueness, accuracy, repeatability, as we talked about today with somebody. Sometimes repeatability is not always the easiest thing to do, from batch to batch, from person to person, technician to technician, from instrument to instrument, from lab to lab. It can get quite problematic. Your LODs, your limits of detection and quantification on your instrument. your method limits of detection and quantification, which are different. It's the whole method that you are using as opposed to what the instrument can do. Instruments are usually good at doing many things and they can do it well. But if your whole extraction method, especially isn't used internal standards, isotopically labeled internal standards to help quantify what your losses are like, what your extraction efficiencies are like, MLD, MLQs become the most important thing that you need to report on. So not just what the instrument can do, what your method does, right? Unless you do what's called direct injection. We'll talk about that later. Oh no, there's more. So you have to do linearity. How is your calibration curve nice and straight? Does it plateau? Do you want to accept the fact that it's plateauing? Do you want to do a quadratic equation? Or do you want to try to change things to make it linear? It's up to you, right? Or up to the criteria. You have working range, matrix effects, extraction efficiencies. Can you just extract something with 10 mils of methanol for 10 minutes? Or do you need to do it for 20 minutes? Do you need to use 20 mils of methanol? Do you need to do sequential extractions? Like when you need to quantify how little time and how little effort do you want to get a really good result? And that's usually to maximize your time. Ruggedness. Can you change maybe 11 milliliters of solvent instead of 10, maybe because you screwed up or because you accidentally did something? Will you still get repeatable results? So ruggedness is very important because it happens in real life, right? So lots and lots of cooking. So let's get to what the heck is Alistair talking about? So ultraviolet filters for the type of chemicals that I'm studying, amongst many others, they're usually used at quite high concentrations. So when you look at sunscreens, like this is one kind that's sold in Canada, it started at the beginning. Again, holistic question. Everybody uses sunscreen, but there's also personal care products, makeup, lotions. It's in everything. It's in clothing. It's in commercial products, paints, plastic, probably this bench. Like who knows? Like there's additives just to maintain so that things don't degrade by sunlight. Right? So commercial products, but also to protect you from a toxicological perspective for cancer or getting sick. It's very important, right? We all wear sunscreen. So they're by design resistant to degrading sunlight. That's the whole point. But not all of them work across the whole spectrum. So you'll have certain chemicals. So here, there's no laser. So you'll have one certain kind with the red line, one certain kind with the blue line, one certain kind with the green line, which is zinc oxide, which is an inorganic version, will be able to absorb sunlight at different wavelengths. So lots of the times, you don't just find one. You go to sunscreen, you'll see like 4. And so they combine them together so they can cover the whole UV spectrum to protect you. So it becomes very, and these are at like 3%, 10%, 15% formulations. So we're not talking about parts per billion, parts per quadrillion kind of levels. These are significant levels. And so it's important that you're going to have the washing off of these materials off of your skin or from different products degrading in landfills or who knows what ends up in the environment at significant levels. So we need to figure it out. Why do we care? So endocrine disruptors, estrogenic, reprotoxic, nephrotoxic for your kidneys, neurotoxic for different neurological systems for various other organisms in the environment. Can affect reproduction, fecundity, they call it, right? Currently, there's very little freshwater data in Canada. These are very common to look at in coral reefs, like in Maui, Hawaii, Florida, Palau, New Guinea, those types of places. They've banned oxybenzone, which is one kind of ultraviolet filter, but there's many, many other ultraviolet filters, right? And so, but freshwater data, there's very little known about it because we don't normally grow corals, and that was the primary concern before. They were noticing the bleaching of corals. So we have a major river that comes from the United States that flows through the middle. I'll show pictures later about where we sampled the beach, and it discharges into a major lake. And our lake is only 2 meters deep. It's a huge lake that's thousands of square kilometers, but only maybe 2 meters deep. So eutrophication problems, blue-green algae, things like that. But also chemical contaminants can act very strangely in that type of an environment. So we need to figure out how much is being used by people for wastewater, what's being discharged into the main river that's coming from our treatment plants, what are the threats to aquatic life that live there, The threats to human health, because if you're, especially even in a swimming pool environment, yes, you've got it all over your skin, but now you're going to be taking it in and swallowing it all the time. So how much levels are staying in swimming pools all the time, right? So ingestion from a human tox perspective as well. So that's important. This is to illustrate that there is wide degree of, is that what this is for? Is that what it's for? Yeah. So you have log KOW, right? Hydrophobicity, right? So the higher the number, so 7.35 of the suite of 8 that I'm using is the most hydrophobic. So you'll have comparatively the lowest water solubility. So around 4 ppb, right? 4 micrograms per liter, that kind of thing, is the water solubility limit, and that will matter later. But then you also have salicylbenzone, very hydrophilic, 0.88 log KOW, 52,000 milligrams per liter, so quite a high solubility. So it depends on your compound. So we have oxybenzone, the one that they like to ban, and octinoxate and octocrylene, which is one that ecotoxicologists are starting to become more concerned with for a variety of reasons. So, summary of our studies that we're doing was the analytical method validation. I'm not going to bore the heck out of you with that, but it's still very important. In wastewater, surface waters, and chlorinated tap water, so different methods slightly. Wastewater epidemiology, how much is there? Outdoor pools, rural beach, and now mesocosm kinetics experiments. So sort of a linear train of thought, like thinking, right? So everybody's favorite, solid phase extraction. It works very well, takes a lot of time. And so has anybody here done it before? Anybody done solid phase extraction? Yeah, I got a couple nods. Do you like doing it? Great, put on the music and then do it. Yeah, nobody, don't touch your phone, it's good. So we have, this is level 2 biohazard containment. We're doing wastewater. Very nice to have foot pedals for water when you're washing things is a nice feature as well, instead of touching everything with wastewater. So basically you take wastewater, so you take the water inside of jars or inside of these bottles, depending on where you're coming from. These sippers, these straws will then put the water, drip them through the sorbent that's in here, go to waste. You can throw the water out that comes out of the chamber, and whatever is left is stuck to these little things of sorbent on the inside, and then you can elute those compounds off using various organic solvents. Then you can reconstitute them in what you want, shoot them on GC, shoot them on LC, whatever it is you want to choose. So that's our LC triple quad that we have there. It's not the Princess. It is a 6470. It is not 6495, but still middle high ground for your money. It's a good machine, but also very similar LC stack to what you have. So we filter the solids, dechlorinate the waters using a certain guidelines from American Water Association using sodium thiosulfate, so a sulfurous kind of compound to reduce ions. And then pre-concentrate your analytes using SPE, 6-point internal standard calibration curve. And the nice thing about these instruments is they do what's called polarity switching. So you can do positive mode, negative mode, and it can read it very fast. So you can just run them all in one mode. When I started out when I was younger, for some reason, we had a 6410. If anybody knows what that is, from Agilent. You have to run everything in positive mode, and then we would do a whole other batch with calibration curve and anything in negative mode. Now we just do everything in one big mixture. It's good. So, to give you an idea of why internal standards matters, is when you put internal standard, depending on your process, you will be able to gauge what your losses are to that process. So pre-SPE, so at the very, very beginning, you take a jar of water from a river or from a mesocosm if you want, you spike it with internal standard, then everything that happens to that internal standard in that water should be similar, in theory, right? So if you spike it post SPE, so you run it through that chamber before, like I showed you on the picture, and then put the internal standard afterwards, you might have some losses to that sorbent or to the chamber or to the sippers, those straws, or to the jar of water originally. And if you put the internal standard afterwards, then the rest of the procedure will follow the internal standards losses. So the difference between the two is from where you spiked it before and after. And so what this is showing is for this particular compound, which is avobenzone, and if you talk to people who know ultraviolet filters, it's a very problematic compound. It doesn't like to play nice. If you were just to go, I'm gonna take water, extract it, put it into LC vial, then put the internal standard at the end because I want to be judicious and I want to get a better signal and that kind of thing. Look how much what you're going to quantify. So we think it's supposed to be 25 ppb, micrograms per liter in the jar when you're validating this for this method for accuracy. And if you were to extract it and then put the internal standard at the end, it thinks you have 1. So it's really, really important to have that internal standard experience the same losses as you go along. So that's the importance of using internal standard. And so if you put them at the beginning, you'll have recoveries of like 104, 97, 98, 105, 112. 75 is on the low end of acceptable, but still acceptable. 86 and 80 for all 8 of those. So it's good. Okay. So for wastewater, we want to know how much are we using. So great idea. So whether it comes to, especially when it comes to, let's say, illicit drug use, you'll have I met with chemists from Czech Life Sciences and then Masaryk Institute in Prague yesterday. There's one woman, she's known as Drug Lady. That's what they call her. I'm like, hey, Drug Lady, very nice to meet you. But she's really knowledgeable, looked at many, many different illicit drugs, festivals, and when events happen in Prague all the time, they'll see these spikes in the illicit drugs go on in the wastewater. The best way to figure out how much people are actually using without having to worry about prescription rates, getting private information from people, all that kind of stuff, right? It's just what's there. It's wastewater. So it's exactly what's being put in there. So really good idea. The best idea you can get as a surrogate for human usage is from wastewater epidemiology. So we looked at 2 seasons. We looked at winter to summer because you're thinking if it's sunscreens, where I'm from, it goes from like right 2 days ago, it was plus 42 in Winnipeg, in the center of Canada. Tomorrow, it's going to be 0 and snowing. So in the winter, it's minus 30, minus 40 for a good 6 to 8 weeks where I'm from. And so you wouldn't assume people are going to be outside wearing sunscreen. So let's see if there's any differences in the wastewater, see what those trends look like. And so we looked at the primary effluent, which is going into the treatment plant, after the secondary process where they use oxygen, microbes, sludge, mix it all up. They call it the mixed liquor. Not the nicest thing in the world. And then see what the final effluent looks like after tertiary treatment, which is a UV process. So not UV filters, but the actual shining UV light to try to kill microbes, see if that affects photolysis, so photolytic degradation and transformation prior to being released to the river. Let's see. So this essentially from our main treatment plant, this plant services approximately 600,000 to 700,000 people, and it has a flow rate of about 250 million liters a day. So 1 or 2 ppb, parts per billion, or micrograms per liter, can end up equating to like 1 kilogram of any particular compound reaching the river across the highway every week. So for instance, you might have heard of sulfamethoxazole, which is a antibiotic. If you look at sulfamethoxazole and you look at acetylated and glucuronide, so different metabolites from the human body of sulfamethoxazole, and you add them up, it works out to about 2 kilograms every week of one antibiotic is ending up in the river. And that matters for things like antibiotic resistance and things like that as well, right? So, and that's just one compound. And then you think of all the pharmaceuticals that people use, all the pesticides that people use in their daily life, whatever it is, all the personal care products, add them together, you know, have cumulative mixture of a significant amount of chemicals in general. I mean, it's a wastewater treatment plant, so, you know, duh. So you go into this grit house. Essentially, it will filter out bicycles, condoms, all garbage, things like that, tree branches, and then truck it away. And then it will go to a primary clarifier. So we have outside ones, and then we also have inside ones because it's freezing cold half the year. So, And then we, of the whole process, we will have anaerobic digesters. And from a sustainability standpoint, we will take the biogas that is generated through methanogenesis and methane, things like that, different gases, and they use it to heat the plant. So burning things is not great, but burning natural gas versus burning biogas, you have to burn some kind of gas in order to heat this place because it's freezing. So you supplement burning the biogas with some natural gas, so to heat the plant. So relatively as sustainable as it's good. So it's good. And then it will go across to the aerobic reactor, add microbes, come back across to this little plant here where there's 1,008 xenon bulbs that glow crazy bright green, and we'll try to kill as many microbes as possible prior to going across the highway to the river where it then discharges. That's everything you didn't want to know about a wastewater treatment plant. So let's take a look and see if I can walk you through that. How do I keep putting this down? So we have mass load. So instead of concentration, right, of parts per billion, because it varies because the concentrations are vary on flow rate, right? That goes through the treatment plant. So we multiply it times the flow rate to get mass. How much is mass is hitting the Red River, our discharge? So we've got mass load in grams per day. And then we have primary, secondary, final, primary, secondary, final. So all the different steps of the treatment plant for all of the compounds. And this is summer, and then this is winter. And this is going from 0 to 120 grams per day. So what you see here is there's a compound in pink called silisobenzone, the most hydrophilic, the one that likes water, the greatest from summer and winter. Oxybenzone, which is this weird shmooey green color here, which is down here, is the one that's banned in Hawaii and Florida and places like that, but it's still there. And what we note is silisobenzone is the greatest and not in sunscreens. So even though even though it's the greatest amount, it's not found in any of the sunscreens that I surveyed about 100 sunscreens before I did the whole experiment. So it's coming from somewhere else, paints, plastic, who knows what, like where it's coming from, right? But it's the greatest. Dioxybenzone, these ones here, these orange ones, and homosalate over here are removed to a certain extent. There's these little mean pluses here, but not too well. And from summer to winter, we see significantly less silisobenzone, avobenzone, and homosalate in comparison to the summer. Also, these little stars mean. So, but overall, no real change. So essentially no change from the beginning to the end of wastewater treatment overall. And even though there is some, and less silisobenzone, avobenzone, and homosalate from summer to winter. And those are all found in sunscreens. This suggests, though, that there are other cosmetics, shampoos, they actually market hair dye, right? For people, they have UV filters in them on purpose to maintain the bright color. We use our hair dye, it's the brightest. And they put chemicals that will live in your hair. So anyway, you're already using dyes, so it's a chemical, but they add more chemicals. So there you go. Personal care products and other major contributors, because Winnipeg does not use sunscreen in the winter, but there's still significant amounts even in the wintertime. So that either means it's coming from a different source, or it could mean that it's being recycled through the treatment plant through the activated sludge process, because you take this microbial sludge and then you bring it back and you react it with new wastewater, and then you bring it back and you react it with new wastewater. And it does a really good job of settling out all of the sludge and the solids. And one of their goals as a wastewater treatment plant is to reduce your solids by 95%. That's one of their criteria prior to being discharged to the river. And then biologic oxygen demand and other things. But so it's a really simple process for anywhere between 200 to 350 million liters a day to just return activated sludge. But it could recycle compounds. So silisobenzone is used in plastics, paints, dyes, and could be from other commercial products, but we don't really know. So they don't always tell us. I'm gonna drink some water. So, so significant cumulative masses can be released, depending on the concentration, depending on the flow rate. Why do we care? You learned about hazard quotients, ecotoxicology. You teach that here? Yeah? No? Yeah? No? Yeah. So really simple. The simplest way to be able to screen and triage for not only human toxicology, but ecotoxicology. In our country, Health Canada has, as a major federal jurisdiction, they have what's called Tier 0 human risk assessment and Tier 1 ecotoxicological risk assessment. They basically mean the same thing. How much exposure could you have in the worst case scenario? So in our case, what we like to do is use the final effluent, what's being discharged from the treatment plant to the Red River. Over the whole season, we just pick the highest number that we had seen, you put it in the numerator, and then you take the toxicity to the most sensitive organism using either structure activity relationships or using actual toxicity data, or both. And in general, you'll find that chronic toxicity values are usually the lowest. So you put the greatest situation of exposure, the lowest number of toxicity, and you will hopefully end up with the greatest hazard quotient. Really simplistic, does not take a bunch of things into consideration. And what's really important is when you generate a table like this, maximum concentration hitting the river after the process, the toxicity that you get from the most sensitive organism, and in this case, the Daphnia, green algae, fish, Daphnia, and the C indicates chronic, or instead of acute toxicity. And then you end up with these maximum hazard quotients. Anything that is greater than 1 merits further investigation. So a hazard quotient that is 1 and a hazard quotient that is 100 does not mean that the compound is 100 times more of a concern. It just means you should really be looking at it. So it's very conservative. You can't read a lot into it. Very good way to triage things of importance. So you see things like this, like salicylbenzone, even though we had the greatest concentrations in the water, it has one of the lowest toxicity, or greatest toxicity, lowest toxicity. So you end up with hazard quotient of 0.0049. You look at that and go, it doesn't really merit further investigation, even though there's lots of it in the water. Doesn't mean that it's not a problem. It just means that if you had to screen really quickly, you could do that. Ones like octocrylene, however, it has the lowest water solubility, and you're going to find the least of it overall, but it has one of the lowest numerical values for toxicity for fish and has a hazard quotient of 230 without even using what we call conservation or uncertainty factors. So multiplying this number times 1,000, the EU does that quite a bit. European Union will take this divided by this and times 1,000 to be very conservative, to be very protective. Now you're talking about 230,000 for octocrylene. So it really means pay attention to this. Maybe you should look at that compound. And so the EU right now actually is becoming far more concerned with this compound as opposed to oxybenzone, which is what the beaches are eliminating for coral. So that's how you triage. And in general, the greater the hydrophobicity, the greater the risk, because the greater propensity for bioaccumulation, bioconcentration, biomagnification, things like that. Right? Is he done talking yet? So we now know how much people are using, how it's getting into the treatment plant. We don't really know. We know how much is going to hit the river to be care. So we want to know what are our aqueous concentrations for this particular experiment for the entire summer. The outdoor pools in Winnipeg, they open usually at the end of June and they close on what's called Labor Day, our first main weekend in September. And then they close the pools because where I'm from, it can go from plus 30 at the end of third week of August. 2 weeks later, it will never get above 10. So it just, the switch gets flipped and it gets cold. It's weird. Sometimes it doesn't work out that way, but lots of times it does. So we were able to monitor before anybody even went there, all the way to the very busiest week of the last week of the year. So there you go. So we wanted to know how these levels would vary over a week based on usage, how it would work over the afternoon, oh no, we had to pay a student to sit by the pool all day and get samples and report to me. So even students who are second year students are able to work in our laboratory. If you're keen enough and you don't break all our instruments, you can work in my laboratory. But yeah, you have to sit next to a pool all day. I'm sorry. So, but you can't wear sunscreen. So you're going to need lots of pivo, and you're going to need lots of shade, and you're going to have to hide something. Anyway, so we're very conscious what we call aseptic technique, not only in microbiology, but very important for trace organic contamination in my laboratory. Because I'm wearing lotion, I don't know if it has a sunscreen. I've now touched my bottle, and now I'm touching this thing, and who knows who touched this before me? Now I got UV filters on my hand. You just don't know, right? So you need to be very careful. Sampling locations. We are about 800,000 people, not a huge city, but very spread out, very flat, prairies, agriculture, 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 everywhere. That's what it is. So I'm in soil science and agriculture, doing environmental things. And so we have three main outdoor pools. Our university is down here in this bin. And so we have near my house, and then we have the eastern part, and then we have northern part, and they are overrun with people all the time because it's something for children to do. It's outside, it's not minus 40. Let's all hit this pool, right? So significant usage. But also about 50 kilometers south of our city, we have a man-made beach called St. Malo. Man-made, but also very big, but also absolutely overrun with people. Just a significant amount of people that are there. And they even have summer campsites as well. So people will park their trailers, stay there all year, drink beer, eat foods, go to the beach, and put sunscreens into the environment. So there you go. So overall snapshot between concentrations of micrograms per liter, so ppb on the axis here, from 0 to, for pools, 0 to 3 micrograms per liter. And in the beach, about 0 to 0.5. So a different axis. And what we notice is in outdoor pools, none of that salicylic that we usually see the highest in wastewater, but we see this increasing amount of octosalicylates and octinoxate, but octocrylene is the most hydrophobic compound. So it should like soil, it should like sediments, it should like dissolved organic matter. This is water, but in the water, it shows the greatest concentration of around anywhere between 2 to 3 parts per billion. But its water solubility is only 4. So it's right up near the limit of what its water solubility is, but its log KOW is 7.35. So it was really weird for me to see how is this such a hydrophobic chemical being continuously resuspended within a water environment, in the pool. In the beach, we see the opposite. We see oxybenzone, which is what they're concerned in a beach environment, like in Hawaii, right, in Florida, places like that. So you do get this high amount of oxybenzone at the beach, and much less octocrylene. We're talking about 0.05, 0.1 parts per billion, so order of magnitude less. So totally different trend, right, to what you see within a pool environment, what you see in a natural environment. And so, yeah, and so oxybenzone and homosalate, which is also found in like the 10 to 15% level in sunscreens in Canada, what it's registered for. So we should see a significant amount of homosalate. Then we also see that here as well. So it was interesting to see very hydrophobic being continuously resuspended in the pool. So this, if we look at over a week, unfortunately, students don't work on the weekend. So Monday to Friday, they're like, after the weekend, usually maximum amount of people, there are people lined up at the gate trying to get in, so it's massive amount of people. So you have a lot of very high concentrations of even octocrylene. This is 14 ppb, which is way above what its water solubility limit is supposed to be. And it was just because we were trying to think of it, it's just this forced recirculation. So it's not really dissolved in the water. It's just suspended in the water, which is such a bizarre phenomenon. So it's this constant forced recirculation, this very influential jets that they have inside. They're very new pools, so they have very strong circulation systems were quite high. But most of the compounds overall were at elevated levels at the Monday after the weekend. And then it drops around Tuesday, and then it would pick up. And then for some reason, we weren't able to see octanoxate after that. So that was the kind of trend that we saw in the pool over the week. But then comparing over the afternoons for usage in a pool environment, we reach a maximum. This little 0 represents noon, like lunchtime, 1 p.m., 2 p.m., 3 p.m., 4 p.m., or I guess 1300, 1400, 1500 in Europe, whatever way you look at it. So both pools and beach reach their maxima around 3 p.m. Makes sense. Most sunscreen usage, most amount of people are there. And overall pools show an increase and then some sort of a decrease over time as you get closer to dinner time. People are leaving and there's less usage, or it's all worn off and people don't reapply. But beach shows until about 2 or 3 p.m., and then a lot of them plateau, except for octocrylene here, and avobenzone is a little bit of a drop. But we're talking about a difference of our axis of 0 to 5 parts per billion and 0 to 0.5, so order of magnitude less in the axis. So you'll get sort of these sort of plateaus that will exist as opposed to up and down, indicating that there's probably dilution is going to take place overnight. So overall, the greatest mean concentrations or average concentrations was the most hydrophobic in pools, the octocrylene. Benzophenones, oxybenzone, the one they were concerned about, is one of the lower ones. For circulation and less organic matter. So as I was speaking with other chemists and biologists here, sometimes inorganic photolysis, so photolytic sensitization of dissolved organic matter or other ions within the water can then start to chemically react with your contaminants. So instead of direct photolysis, you can have indirect photolysis. But with less organic matter within pools, you might have less of that mechanism as well. But we don't know. And in the beach, oxybenzone, the one they were concerned about in other places were the greatest levels. Octocrylene, that was huge, is much lesser here, suggesting that absorption to solids, dilution in the environment over time, or indirect photolysis could be important processes. So especially given the intraday plateau and the persistence, dilution is starting to suggest that that's going to happen. Because if you come back the next day at 11 a.m. or 10 a.m., you'll probably find it. So you've seen your mesocosms nearby, right? Anybody seen your mesocosms here, university? Anybody seen them? I saw them. They're awesome. They're great. I love them. Different from ours. Ours are giant tubs, sediment, soil, submerged macrophytes, duckweed, wild rice studies we're doing with indigenous wild rice. But these ones here, they have nice aeration systems and temperature probes and heating. We can't heat ours. We'll destroy them in the middle of the winter. So really nice network to combine with your university and ours to get different kinds of data, different mesocosms. And also look for consistency as well. Very important. Right? So we dose 6 mesocosms in triplicate, 2 different treatments, one in just water, and periphyton, and algae that grow in there when you don't want them to, and sediments and plants. And so we had 4 representative compounds representing a spectrum of hydrophobicity and solubility instead of doing all 8. And instead of having to do SPE, we just direct injection. So we're like 50 ppb, 1 milliliter, or 900, 1 milliliter, 20 microliters of internal standard. Push it into a vial, run it. Thank you. I don't have to do this giant process. And we can see what the kinetics looks like. So not incredibly environmentally realistic because it's a little bit higher, but not like 1 order of magnitude 2, but to get a kinetics constants and half-life off of it to be predictive and help us. We also deployed sediment jars at the very beginning of the experiment. So very uniform sediment, 5 to 10 centimeters, embed the jars with the exact same amount, uniform across, and every time we take water samples, we're very, very careful, pull the jars out, decant them off, freeze dry them, then we're able to do extractions for concentration in sediment. And we also were partnering with another organization to see if there was sediment DNA changes as well in exposure to these compounds. And it was just completed like 2 weeks ago. That's great. So we have to go through the metadata now, which is good. Those are our big tubs, essentially for horses, for feeding, right? But it's, you bought them new, and you can see them on all sorts of different things. This is Pepe Rodriguez Gil. He's from Spain, but he's a researcher at the Experimental Lakes Area, IISD, or International Sustainable Development federal organization. We have an area called Experimental Lakes in the center of Canada, which is literally like 47, 50 lakes that are made out of granite. So they're not going to leak into the environment. You can do full lake. So you go from mesocosms to full lake mesocosms, essentially. And you're able to, we're going to be dosing them this year with UV filters, but through workers using consistent application rates, masses on people. They will use the sunscreen all day. Then we tell them to drink beer and hang out in this pool all day in this lake for X amount of time, very consistent, and see what kind of washing rates comes off and see what those concentrations look like in a realistic scenario over time in a larger lake. So that'll be kind of realistic. Good. So opportunity, they're always looking for opportunities. We're working with the Experimental Lakes area with Rwanda for pesticide screening right now for other African and European countries working with us to start to do bigger projects like that for FATE studies. So really good idea to get an idea of what FATE looks like in a scale like this before you spend a bunch of money doing an entire lake. So it's responsible. Right? And so stabilize them for a couple months, get rid of the chlorine from the tap water, let them establish, grow some things, make a master batch of all 4 UV filters at 50 ppb, then split them so they weren't individually made, so there's no variability, same concentration. Sample at 0, 12, 24, 40, 96 hours, then weekly for 9 weeks. Collect a 1 cup of water and then the sediment jars, immediately extract them, no freezing, no storing them, run it. Like just do it because it's kinetics, right? Direct injection, great. What do we see? Silicybenzone, so red and blue are silicybenzone. So the red is the silicybenzone sediment treatments. The blue is silicybenzone in water alone. Oxybenzone was in green in the sediment, and then oxybenzone in purple with just the water treatment alone. And so similar kinds of trends over time, but what we see is silicybenzone is more persistent for the first week, sticks around, more water soluble. Oxybenzone starts to dissipate quickly in about 96 hours. And we'll get to, so is it a concern for people? Is it toxic? Is it soluble? If it goes away in the first week, is it really a problem, right? Octocrylene, as you show here, regardless of the type of treatment, its solubility limit is about 4. So it usually stayed about 1 to 2 ppb the entire season. And in fact, when we had overwintered the mesocosms, we sampled in the spring again about 3 weeks ago, we found that the concentration was the same still, even over the winter. So that was interesting. And then octosalate, we weren't able to quantify. So something else is going on with this other compound where it must love to stick either to the surface of the water, so superficial sticking, surface tension, or it'll like to stick to the plants or get uptake by plants or stick to the plastic tubs. I mean, who knows what's going on? But we weren't able to do that. And that's science, right? We failed wonderfully. It gives us data. So the conclusions are silicybenzone levels are greater than dose, indicating that they're used maybe in the plastic tubs because it was slightly bigger than what our 50 compound was, but they don't tell us. I don't even know if they know what they use in their plastic, right, when they make it, but somebody does. Zone dissipated the fastest from the sediment and plant treatments. Initial levels were half of what we were expecting right off the bat, indicating that there's some partitioning going on immediately as soon as we dose it. Dose oxybenzone, boom, it's going to go to the plants, stick to stuff, be an oily mixture and do weird things. Or maybe resistance to some photolysis. First order kinetics and half-life. So for oxybenzone, between water and the sediment, respectively, 3.6 days, 2.9 days. Silicybenzone, about 30 days and 17 days half-life for these compounds. And that's for the non-water. So the ones that had sediment and plants showed a much faster half-life, much faster dissipation probably due to not only absorption mechanisms sticking to stuff, but from other things as well. Who knows? Maybe a lot of indirect photolysis, a bunch of other gunk in there as well. Who knows? We need to figure it out. So we got to measure our sediment concentrations. Where had a student validate all of that criteria about how to get the sediment concentrations off. Then we can start to calculate partitioning coefficients, be predictive, start to give us a better idea of risk for these compounds with animals and organisms. And we look at the sediment DNA, see if that changes anything. So we didn't really see much sediment DNA changes over the season, but we haven't run the spring data. So we have to see whether or not our spring, same sediments that were there over winter. But what we did preliminarily notice that I don't have on here is after the winter and the spring, some of the compounds went back up again. And that was probably due to everything dying and then basically cycling it back into the aqueous environment. So not being transformed, maybe it was stuck to the plants before, but now the plants are all dead and now they're detritus. Now they're back into the environment. So maybe that's indicative of what could be happening in real life as well. Who knows? So maybe that's a problem. So overall, when's he going to stop talking? Organic UV filters, they're present year-round in wastewater. We don't really know exactly where they're from, but we use them all the time. So they're what we call pseudo-persistent. More hydrophobic UV filters are persistent in pool water, which is such a bizarre phenomenon, but it really has to do with the recycling effort and lack of organic matter. Or circulation and lack of organic matter keeps them suspended, and intraday shows they peak in the midday and then decline later somewhat. Suggests that there's some removal of UDFs through that chlorination process, and we haven't. And actually, that's what a future student's going to do in my program is look at hydroxylated transformation products from maybe common sources of benzophenols or whatever, and see how much is there. Target them, non-targeted analysis, targeted analysis, be able to calculate risks on that as well. Disinfection byproducts, that's a knowledge gap. Knowledge gap on how oxybenzone persists in beach water. Intraday levels in the beach show less dissipation over the day, suggesting we have to wait till overnight for the water to wash out of the beach area to get out into the lake. And we need to figure out those transformation products. More hydrophobic UVFs and mesocosms aren't readily soluble, so they stay consistent all year. Half-lives are shorter for soluble ultraviolet filters with the sedimental plants for reasons I've already mentioned, absorption. Give some predictive powers. Look at whether or not sediments and plants are either uptaking these compounds like they're shown to do for pharmaceuticals and other things like that as well. They're known to do that. Or stuck to them. And we need to see if this data holds true at our full scale at our lakes area. So that'll be interesting. And there's lakes near my house. So come to Canada. I was talking to you earlier. Lakes. That's actually right outside. We have an island in this place called Lake of the Woods. Beautiful. That's 5 o'clock in the morning. I'll say hi to you. This is where I train my kids mountain biking. There's hills nearby in our city, and that's the same place there. So 5:30 in the morning isn't the worst thing in the world sometimes. Thank you.
Thank you very much for a very nice presentation. And there is time for questions. So if you would like to ask something,
Can I shake the stick?
do you have this in Canada?
My former PhD advisor used to have an arrow because he was big into archery. And I'm like, why are you trying to scare people with an arrow all the time? Yeah, so not as a rule, no, we don't have. It's Friday, everyone, I guess, out here. Yes, sir.
So I want to come back to the. Not really.
Okay. Go back.
Water treatment plant.
Yeah.
So there is a part when there is a UV disinfection.
Mm-hmm.
Those UV filters. Like
are they blocking? Right. Yeah, I don't know. It's a great question. So are they doing what they're supposed to do, which is block ultraviolet rays and help prevent disinfection? That's a really valid process. That's a valid point. So yeah, to look at not only coliforms and BOD and things like that would be very interesting. We don't do that, but let's do that. Yeah, for sure. Yeah.
Common in Canada that this UV filtering of UV
Treatment.
treatment is all the wastewater treatments are with this step or not?
Not all of them. They just are. That treatment that we have at that particular main plant has only been doing that for 20 years. So there's been a solid 100 years where we do that at all. One of the main things was we have what's called a wind grow program. So very common to use sludges from wastewater as fertilizer for farmland, agricultural land. And so to try to reduce the amount of microbes that are going to be applied to agricultural land, so they started to become more concerned with that sustainability aspect to protect it. So more common now, less common when I was a kid. But yeah, but not everywhere. Usually for bigger plants. Yeah.
Thank you for that very nice presentation. It was interesting to see the results of this Miller custom experiment.
Yeah.
Great information. Are there any other studies in simpler setup, more simple setting that you can see where it goes? Because in this one, it's quite complex, right? The Miller custom experiment, it has soil, plants.
But the other variable, like the other ones were just water. But then you're in water, you're going to grow periphyton and algae naturally from the environment. But we only had water at the beginning.
In your system, would it be possible to go for mass balance, to collect all plants?
Yeah, we're going to find.
Everything that is on the surface, all the biofilms.
Yeah, so it's a great question. So this year, we're actually going to set up a couple of mesocosms and try to do a superficial testing as well. So we're going to try to use almost like some kind of a stick and just basically try to pull off X amount, and whether or not it could be in a flask environment or whether or not a microcosm or whether it could be mesocosm, and see how much is on at certain time points surface versus middle water, and then also sediment, and be able to see if we can get a better mass balance. But yeah, more students can do that.
Basic question: what is your hypothesis behind this DNA sediment DNA analysis?
My hypothesis, I think, I don't think anything's going to change. That's what I think. But you have to do the study to do it. I think, as for many people here who do sediment DNA or do soil DNA or water DNA, we have structural and functional redundancies built in. So you have entire classes of microbes. Even if one particular strain or two could be affected by chemicals, it doesn't mean that the ecosystem services are not going to be compensated for by the same class of microbes, different strains. So if we do see differences, it could be at strain level, but probably most likely not at class level. That makes sense. Yeah. Or who knows? Maybe I'm totally wrong, but that's what I think. Yeah.
I just a question because you show the risk quotient and it uses the lowest BNA or sound. I guess it's a part of the those constant values. So I guess it's more or less like a Denny or some kind of this regulatory broadly used fish. How does the relevance of this warm temperature or warm water living species in native species?
Well, I guess so.
Yeah, because that's just thinking, because we found a great difference between what's the easiest to get for toxicologists. So it's Danny already or Medaka or whatever. The relevance to the species you want to protect.
If you want to do more robust, accurate, so one of the probabilistic environmental risk assessment of using species sensitivity distributions with exposure distributions, protective versus 95th centile, you're going to get more, incorporate the variability of toxicity to various species is going to be much more accurate. But when you're just talking about a first tier look at just trying to triage what's important and what's not, I guess hazard quotients are one of the more simple things to do. But there's no question that having more probabilistic distributions of as many species as you can to be more accurate is definitely true. For instance, if you're going to do even toxicity studies with Daphnia, we find that Stereodaphnia dubia is very sensitive to lots of compounds, and whereas Daphnia magna is much more resistant to issues, and so even by orders of magnitude concentrations with lots of compounds. Not that it stays that way all the time, but yeah, it's sometimes, I guess what they're looking for are data in ECOSAR from real experiments, but also a set of rules using various activities to be able to guess as best as it can for compounds that either transformation products don't have that data, or if you want to add to the experimental data for a weight of evidence to try to get a better mesh together of experimental and data.
Just touching, this the poisoning of sulfonites in North America, right? This tire, this tires, compounds, the stabilizers, again, they are quite sensitive. They are toxic only to salmonids, not to other species.
Yep.
So that's the just this the kind of the estimation
Yep.
to lead you to somewhere else. And I'm just if you have anything that's from environment studies, I think from lakes or something like that.
So much less. So really, like where we're from.
The ratio in Canada.
Yeah.
It's like a field experiment, a little bit different than here.
100%. We basically have none. So yeah. So it was for myself to do the freshwater data. Joël, he's a friend of mine. He does UV stabilizers, and he works in a university called Rimouski in Quebec, so more eastern Quebec and French Canada. He does a lot of lake exposure, and then they do things like that, but very much not on the prairies, any other places in Canada. There's a couple groups, one in Calgary here and there, but it's very underdeveloped at this point, but becoming much more common. Yeah. But also to speak to ECOSAR, that's why I showed those hazard quotients without uncertainty factors. Yeah. So a lot you're going to have, depending on the jurisdiction, you can have uncertainty factors of 10, 100, 1,000, and then it completely changes how conservative that estimate is, right? Yeah. Yes.
One more question.
Sure. Yeah.
You are working with, and you presented that the main source of the environment of these filters is the wastewater, right? Wastewater.
We would assume so, yeah.
And it's, I heard about UV filters and those compounds like 10 years ago, for the first time, and a lot is done on this. Would you still consider it as a significant environmental pollutant, or are there some emerging pollutants currently? Which could have the current attention.
So you're saying, is there research better than mine right now?
No, if there are some new compounds used.
There's always emerging new compounds all the time. In terms of, but for what we're doing from freshwater data from our systems, with the types of hydrology, with the types of ionic strengths, the types of organisms that live where we are, it's just an unknown. So for me, it was just something that started from an observation for me, and I felt not only connected to my family, but also connected to my land, my area, that it was very, very topical. And so even at CTAC in Vienna last week, this week, a couple days ago, the posters had gone from maybe 3 last year to now 8 or 9. And so not enough to fill an entire session still, so still not a lot of information being done in a non-ocean environment, but increasing now, and everybody's starting to become much more aware. So I would consider it still topical and still important. Otherwise, I wouldn't do it. But but it's not the only thing that I do, and it's not the only thing that normally everybody does. So there's many other. It could be perfluorinates, it could be illicit drugs, it could be pesticides and transformation products, especially in the soil environment. That's a main concern, and in an agricultural society where I am as well, especially biocides as well. We had a PhD student who's working on antimicrobials and biocides, especially from pandemic, all the different quaternary amines and things like that are being used. So that's very topical right now as well. Yeah. Yes, sir.
Thank you for your presentation.
Thank you.
My question is from methodology. Do you use some passive samplers in your studies, in your monitoring environment?
Yes. So We used to use POSIS, right? So organic integrated samplers. The problem with POSIS, as you're familiar with pest samplers, yeah. So it's completely dependent on flow rate, right? And so when you have changing systems all the time,
on process. If you have at least some flow rate is dependent. So the dependence is
if it's an equilibrium,
if it's like a from sample with independent.
Sure. But that's what organic diffusive gradient thin film samplers are great for, right? So DDTs that are adopted from metals to be able to use for organics, then the rate limiting step is your diffusion coefficient from the gel that's on the outside. And so that is something that has become far more increasingly validated for many pesticides, pharmaceuticals, all these types of other things, none for UV filters. So this very much is the frontier for us of what's going on, how much is there, how much is being hurt at what levels. And then when we want to go, right now we're working with indigenous organizations, northern Manitoba, which is very much close to the Arctic, like close to Hudson Bay, very, very remote, very problematic to get grab samples, very problematic to have active samplers be operational and to ensure that they're working. So we are now deploying for metals and for pharmaceuticals using ODGTs up north as well.
So are susceptible to ODGTs?
I'm sorry?
Are you susceptible to detecting pharmaceutical with ODGTs? Because the sampling surface is quite small.
It depends on how long we're going to deploy them for, but I mean, we've calibrated, we had an entire student do a PhD on the calibration of ODGTs for our suite of compounds. John Chalice, so he is working for Agriculture, Agri-Food Canada. He's just moving back from Western Canada back to Winnipeg right now. Did his entire PhD in exactly that and found that very good recoveries and very good.
Yeah, what I'm talking about detection in real cannabis.
Yeah. Yeah. It was a success. Yeah. Yeah. But it also speaks to us, even for ourselves, for our instruments, we're lucking out, I guess, in terms of instrument sensitivity, that we're getting the methods themselves and the instrument sensitivity is quite good. So it's possible to not have to overload it for extended periods of time to get a mass that's above our limits of quantification. So it's working. But you're right, bigger surface area, bigger thickness of the sorbent would be great. Have more chance to do it, but you know, always challenges. The problematic thing for us is, especially for, like, say, Health Canada, I made 171 pesticide method for regulatory methods for our federal government last year. To do passive samplers with that, it's problematic because the compound suites are so different that you need all sorts of different absorbents to be complementary to all these different classes of compound, right? And it's so problematic. But when you have a nice tighter suite of very similar classes, it becomes less problematic. But the treatment plants are great because they have 24-hour active samples. So we get 24-hour composites, 365 days a year. So we get a good representative snapshot. So all the wastewater data is representative of a time-weighted average of 24 hours. So, yeah. Yes.
When I say that one student does all the PhD, just all the innovation. How many people participate on such a project? And maybe are there also masters in the
Yeah.
all of them?
Definitely. So you have masters that are assisting with sub projects. Maybe one can be concerned with pH changes of uptake and things like that. We like to work together with ecotoxicologists as well. So it's very low-hanging fruit for us to be an analytical chemist, but we work with biologists because it's the so what, right, kind of attitude. Great, we see compounds in the environment, so what? So, but with biologists, they're like, we don't have the analytical capability to find out what we need, so we're always working together.
And how many people does all the interest participate?
What kind of project? Like, what do you I mean, so you'll have a particular list. If you had 8 isocosm, we might have a student to do the chemical analyses. If, say, somebody was concerned with emerging insects or that kind of thing, or whatever, you have another student, a master's student, even an undergrad from another program. And so we're constantly working together. It's not, Canada is very, we don't build kingdoms. we like to, we're not siloed. We're very, let's just work together all the time. So honestly, the answer can be anywhere from 1 to 5, you know, it just depends on how many more questions and how much more funding you have to be able to do that. Yeah, you're welcome. We tired of hearing me talk yet?
Thank you very much for a very nice presentation, and I would like to thank all of you for coming and being here.
Thank you. Thank you very much.